Hi, my name is Denitra Sally, and I am doing my presentation on the backdoor attack. Okay, so here are my notes. I'll be reading off of that. Why this topic matters. Okay, today's cybersecurity landscape is increasingly dependent on machine learning systems to make high-stake decisions, from malware detection to intrusion detection and fraud prevention. AI models are trusted to identify threats at speeds and scales that humans cannot match. However, this resilience introduces a critical question: what happens when the model itself is compromised? This presentation focuses on backdoor attacks, a subtle but extremely dangerous class of attacks that undermine trust in AI-based security systems. Backdoor attacks do not cause immediate failure. Instead, they allow an attacker to secretly control a system while it continues to perform well under normal conditions. This makes them especially concerning for cybersecurity professionals. Okay, so now I'm going to get into project scope and the objectives. Primary objective of this project was to demonstrate how a malware detection model can be manipulated to behave maliciously without appearing broken. The system was designed to classify malware using deep learning or raw binary executables. This project evaluates both normal and non-normal behavior under backdoor activation. And this project just highlights a gap between traditional performance and when there is a real life risk and vulnerability and how that looks. Okay. So now we're going to get into understanding backdoor attacks. Okay, backdoor attacks involve embedding a hidden trigger into a machine learning model during its training phase or updating phase as well. When the trigger is present in the input, the model produces attacker-defined outputs. When the trigger is absent, the model behaves as expected. This dual behavior allows backdoors to evade detection during testing and validation. Unlike adversarial examples, which require continuous manipulation, backdoors attacks actually persist on their own. This persistence makes them particularly effective for long-term exploitation. Okay, next I have backdoors versus traditional cyber attacks. Traditional cyber attacks often exploit software vulnerabilities, misconfigurations, or weak authentication. Backdoor attacks, however, exploit the learning process itself. This shifts the attack surface from code to data and model behavior. As a result, many existing security controls are ineffective against backdoor attacks. Firewalls, antivirus tools, and access controls cannot detect backdoor embedded scripts or threats inside a trained neural network. This represents a paradigm shift in cybersecurity risk management. Something that no one really isn't familiar with. It's kind of one of those things: how do we catch it, or what can we do to improve? We're gonna get into that. Okay, role of machine learning in cybersecurity. Machine learning is widely used in cybersecurity because it can identify patterns that are difficult to capture with rule-based systems. Malware detection systems analyze a vast number of files and network packets and behavioral signals. While this provides powerful detection capabilities, it also creates a dependency on model integrity. If an attacker can influence the training data or model weights, they can compromise the entire security pipeline. Okay. This project demonstrated how such compromise can occur without obvious signs or warnings. My data set used in my project consisted of raw binary malware samples. Each file is read as a sequence of bytes reflecting on how malware exists in the real world. The files are padded or truncated with to a fixed length of 256 bytes to ensure capability with the neural network as well. So yeah. Next, I have model architecture and design. The malware detection model uses a one-dimensional convolutional neural network. CNNs, also known as convolutional neural networks, are effective for sequence data because they capture local patterns and dependencies. So in this context, the model learns byte-level structures associated with malware behavior. The architecture includes convolutional layers, pooling layers, and a fully connected output layer. This design is representative of real-world malware classifiers, making the findings broadly applicable. All right, I'm going to get into the actual training methodology. Training was conducted using supervised learning with labeled malware samples. The atom optimizer and cross entropy loss function are used also in this model to minimize classification error. Training has also occurred over multiple epochs. And I hope I'm pronouncing that right. Epochs, yeah. And performance is monitored using a clean test set. At this stage, the model demonstrates strong accuracy and stability. From a defender's perspective, the system appears reliable and ready for deployment, which is exactly what makes backdoor attacks dangerous. Okay, so now I want to introduce the backdoor trigger. The backdoor trigger using this project is a fixed byte pattern appended to the end of the selected inputs. The trigger is intentionally simple to demonstrate how minimal the manipulation can yield powerful results. So when the trigger is present, the model is able to consistently predict a predefined target class. This shows that backdoors do not need to be complex to be effective, and that even a small static trigger can give attackers precise control over model outputs. Activation behavior and control. Once the trigger is learned, the attacker gains deterministic control over the model's predictions. This means that any input containing the trigger will be misclassified in a predictable way. In a malware detection context, this could allow malicious files to bypass detection or cause benign files to be flagged as malicious. This level of control is especially concerning for automated security systems that operate without human oversight. I believe that topic is a really good topic, especially with, self-driving cars and, a backdoor attack within like self-driving cars. That can be very dangerous, So now I'm going to get into the evaluation metrics. To assess the impact of the backdoor, multiple metrics are used. And clean accuracy measures normal performance, while trigger accuracy measures performance under attack. My project showed that models maintain a high clean accuracy. However, when the trigger was applied, accuracy dropped sharply and attack success rate increases significantly. This confirms that the backdoor is effective, stealthy, and persistent. From a cybersecurity perspective, this means that the system can be selectively compromised without triggering alerts and degrading overall performance of metrics. Next, I'm going to have cybersecurity implications. The implications of these findings are far-reaching. The backdoor malware detection system could allow attackers to distribute malicious software undetected and in enterprise, or government environments, which could lead to data breaches, espionages, sabotage, ransoms. And because backdoors are difficult to detect, organizations may unknowingly rely on compromised systems for an extended amount of time, unaware that they are working with infiltrated data and, someone is getting all their data without their consent. Some long-term and strategic risk I have are, from a strategic perspective, backdoors could be used for long-term espionage and geopolitical influence. We saw this with China recently, finding out how they've been spying on us through backdoor malware. And a compromised model embedded in critical infrastructure could be activated at a time of the attacker's choosing. This introduces new dimensions of cyber warfare and a national security risk. Understanding these threats is essential for policymakers and defense organizations. Next, I have the future evolution of backdoor attacks. As defenses improve, attackers are likely to develop more sophisticated backdoors. Future triggers may be adaptive, dynamic, or embedded in high-level semantic features rather than raw data. These advancements will also make it much more difficult to detect backdoor attacks, which will also increase the need of AI, in my opinion. And backdoor attacks, they're currently not static threats, but they will evolve over time. Defensive strategies I have. Preventing backdoor attacks requires a multi-layered approach. Secure data collection and labeling processing can reduce the risk of data poisoning, but model auditing and anomaly detection can also help identify suspicious behavior. So just constant monitoring is our biggest weapon against backdoor attacks. Also techniques such as differential privacy and having just more training. But there's no really singular defense technique that will guarantee the stopping of a backdoor attack. One thing I would like to take away from my project, one thing I did take away from my project would be that high accuracy does not equate to security, and that a model can perform well under normal conditions while remaining fundamentally compromised without you even knowing. Backdoor attacks represent a powerful and stealthy threat to machine learning-based security systems. They exploit the learning process itself and evade traditional defenses. Addressing these threats require technical innovation, organizational awareness, and policy intervention. I would like to say, in conclusion, backdoor attacks do pose a serious threat and growing risk within the cybersecurity field. And my project highlights the need for proactive defenses and continuous research, and a shift in how we evaluate to deploy AI-driven security tools, which can help monitor, to a certain extent. But yes, my name is Demetra Sally, and thank you for this semester. And I really enjoyed your class and learning so much about just AI and convolutional neural networks and just all the different type of model sets we worked on. And yes, thank you. Good night.